Uniform circular motion. The revolution of Earth around the Sun, rotating flywheel, electrons revolving around the nucleus, spinning toys, the motion of a fan blade, revolution of the moon around the Earth, etc. are some examples of circular motion. In all the above cases, the bodies or particles travel in circular path. So, it is necessary to understand the motion of such bodies. When a particle moves on a circular path with a constant speed, then its motion is known as uniform circular motion in a plane. As you can see in the figure 2.36, the particle is moving in a circular path. The magnitude of velocity in circular motion remains constant, but the direction changes continuously. So remember this point. If an object is moving in a circular path or is doing circular motion, then the velocity will always be constant, okay, but the direction of velocity will be changed. So as you can see in the diagram, an object is moving in a circular path. So in this case, the velocity of the object is constant. This one is constant, this one is constant, v, and v. But the direction of velocity at each point is different. Let us consider a particle of mass m moving with velocity v along the circle of radius small r with center O as shown in the figure 2.36. Point P is the position of the particle at a point given instant of time, such that the radial line OP makes an angle theta with reference line DA. This one is the reference line, okay, and the position of an object at any particular time, that is t. This one is the position OP, okay, and it is denoted by r vector, that is radius of the circular path. The magnitude of velocity remains constant, but its direction changes continuously. The linear velocity always acts tangentially to the position of particle. In each position, the linear velocity v is perpendicular to the radius vector r. So you can see in the diagram, each point velocity will be perpendicular to the radius. Again here you can see velocity is perpendicular to the radius. This one is radius. Again here this one is radius and this one is velocity, okay. So remember this point, linear velocity is always perpendicular to the radius vector r, okay. Angular displacement. Now we will discuss new topic, angular displacement. Let us consider a particle of mass m moving along the circular path of radius small r as shown in the figure. You can see the figure 2.37, in which we have a particle which has mass small m, and that particle is moving in a circular path. You can see in this circular path, the radius of this circular path is small r. Clear? Let the initial position of particle be at point A. Initially, the particle is at the point A. P and Q are the positions of the particles at any instant of time t and t plus dt, okay. The P position is at particular time t, and this Q position is at time t t plus dt, okay, respectively. Suppose the particle traverses a distance ds along the circular path in time interval dt. During this interval, it moves an angle d theta, and d theta is equals to theta 2 minus theta 1. The angle swept by the radius vector at a given time is called angular displacement of the particle. So remember this point. The angle swept by the radius vector at a given time is called angular displacement of the particle. Clear? Initially, the object position is at point A. After t time, it will reach at point P. So in this time duration, the object, or we can say the radius vector, swept an angle that is denoted by theta 1. Okay, this one is theta 1 angle. Now the object is moving from point P to Q. It will take time dt. Okay, now in this case we can say the particle or object making an angle with the initial point to point Q will be theta 2. That means this angle will be equals to theta 2. Clear? Now we can say the angle in the case of when the body moving from P to Q point will be theta 2 minus theta 1, or it is denoted by d theta. Clear? This one is the angle swept by the radius vector in between point P to point Q. If r be the radius of the circle, so angular displacement is given by d theta is equals to ds upon r, and the unit of the angular displacement will be radian. So remember the unit of this quantity. Okay, unit of the angular displacement will be radian. Clear? And ds is a arc and r is a radius. Angular velocity. The rate of change of angular displacement is called angular velocity of particle. Let d theta be the angular displacement made by the particle in dt time. Then angular velocity of the particle is given by omega equals to d theta upon dt. And remember the unit of angular velocity is radian per second, and dimensional formula will be t inverse, or we can say t raised to power minus 1. For one complete revolution, the angle swept by radius vector is 360 degree or 2 pi radian. If capital T is the time taken for one complete revolution known as period, then the angular velocity of the particle will be omega equals to theta upon t, or 2 pi upon t. If the particle makes n revolution per second, then omega will be equals to 2 pi upon t, or 2 pi into n, where n is equals to 1 upon t, that is known as frequency. Okay, this one is frequency of revolution. So remember these points. Angular velocity is given by omega equals to d theta upon dt, and the unit of angular velocity is radian per second, and the dimensional formula for angular velocity will be t raised to power minus 1, because the dimensional formula of radian is not defined. Okay, so we can say dimensional formula for this quantity is 1. So the dimensional formula for angular velocity will be t inverse, and t inverse can be written in the terms of theta upon t or 2 pi upon t, and we know that frequency, it is denoted by n equals to 1 upon t, and sometimes it is denoted by f. So in the terms of frequency, angular velocity will be omega equals to 2 pi f. Okay, so just remember these formulas. Relation between linear velocity and angular velocity. Now we will find the relation between linear velocity v and angular velocity omega. Okay, let's see. Let us consider a body P moving along the circumference of a circle of radius small r with linear velocity v and angular velocity omega as shown in the figure. Then you can see in this diagram we have a body. That body is moving in a circular path. The radius of this circular path is small r, and body is moving from point P to Q. Okay, from P to Q, this you can see in the figure. The linear velocity of particle is v. Okay, this one will be the linear velocity at different points, and angular velocity is denoted by omega. Okay, linear velocity is denoted by v, and omega is the angular velocity. Now let it move from point P to Q in time interval dt, and d theta be the angle swept by the radius vector. Okay, from point P to point Q it's moving, and it's taking time delta t. In this case, the radius vector swept an angle d theta. So let PQ is equals to ds. This arc PQ is equals to ds be the arc length covered by the particle moving along the circle. Then angular displacement d theta is expressed as d theta equals to ds upon r. Clear? But we know that the velocity is given by ds upon dt, so we can calculate ds in the terms of velocity v dt. Okay, so in this case we have ds equals to v dt, so we replace this value in this equation. So the value of d theta will be equals to v dt upon r, or after cross multiplying dt we'll get d theta upon dt is equals to v upon r. Clear? Again we know that d theta upon dt is denoted by omega, and it is known as angular velocity. So in this case we'll get omega equals to v upon r. So you can see angular velocity omega will be equals to v upon r, or we can say linear velocity will be equals to v equals to omega r. Clear? In the vector form we can represent it v vector is equals to omega cross are vector. Thus, for a given angular velocity, the linear velocity v of a particle is directly proportional to the distance of the particle from the center of the circular path. For a body in a uniform circular motion, an angular velocity is the same for all the points in the body, but linear velocity is different for different points of the body. So just remember, the linear velocity, that is denoted by v, at different points will be same, but the direction of linear velocity will be different at different points. But the angular velocity will be same for all the points for circular motion. Angular acceleration. If the angular velocity of a body performing rotatory motion is non-uniform, then body is said to possess angular acceleration. Angular acceleration is denoted by alpha equals to d omega upon dt, or we can say rate change of angular velocity is known as angular acceleration. Unit of angular acceleration is radian per second square. So remember this one is the unit and this one is formula of angular acceleration. The rate change of angular velocity is called angular acceleration. It is denoted by alpha equals to d omega upon dt. Okay. Now, if the angular velocity of a body moving in a circular path changes from omega 1 to omega 2 in the time t, then its angular acceleration is alpha equals to d omega upon dt, or we can write it in the form of d upon dt into d theta upon dt, because we know the value of d theta upon dt is equals to omega. Okay, so alpha will be equals to d square theta upon dt square. Clear? And we can write it like this: omega 2 minus omega 1 upon t. The angular acceleration is measured in the terms of radian per second square, and its dimensional formula is t raised to power minus 2.